Okay, so this lecture is regarding, we'll go to the bifurcations that occur in 2D systems. So, as you can see, this is uh, an extension of our study of bifurcations in 1D systems plus something more. Certainly, because it's 2D systems, it's much richer and things look cooler. But essentially, you can reduce what's the most interesting thing happening, and the way we are going to build up our knowledge about the bifurcation in 1D systems is going to be very useful. So essentially the idea is the same, that suppose there exists a stable equilibrium or a closed orbit uh, and the question is that how can they vanish, the equilibrium vanish either the equilibrium vanishes, closed orbit vanishes, or change stability. So the fundamental character of the vector field changes as we vary a parameter. That's the central question. And we studied some normal forms in saddle node, pitchfork, transcritical bifurcations. And the idea was that through a change in coordinates, it's possible to reduce the bifurcation can be reduced to a standard form. So bifurcation in 2D, essentially we are going to study bifurcations related to fixed points, around fixed points, uh, bifurcation of fixed points, fixed points, and also bifurcation of periodic orbits. So that's the idea. So you remember we had the over here in 1D we had the saddle node bifurcation, transcritical bifurcation, pitchfork bifurcation, so on and so forth. Over here we can see that similarly we can have stable and unstable periodic orbits, cycles, merge, like it happened with the saddle node. Two fixed points came very close and disappeared. Or we can have a saddle node bifurcation of cycles, like for example a saddle node bifurcation of cycles. we can have something called as SNIC, or a sniper, which is to say saddle node on an invariant circle. We'll get to it, and other kind of bifurcations. So let's start first with the first guy over here. So yeah, we'll come to that. There are different kinds of bifurcations of periodic orbits, but this was our standard treatment. And what's happening here? This was about the interplay of some eigenvalues. Some eigenvalues, they were some 0 in case of as the eigenvalues journey from less than 0 to greater than 0 or equal to 0, we had the saddle node, transcritical, pitchfork, bifurcations. New fixed points were created, so on and so forth. We'll come to that. It can be about a pair of eigenvalues. This is an example of a Hopf bifurcation. When the pair of eigenvalues become pure imaginary, purely imaginary, this leads to creation of closed orbits. Okay. So let's look at it in detail. First, bifurcations around fixed points, fixed point bifurcations. Lambda equals to 0. Bifurcation. So this will be clear in a moment why I'm saying it's lambda equals to 0. So the first example is our standard saddle node bifurcation. And in 2D, let's say I have this as my system of ODEs. So this is just a damping in the y direction. And if you look at it, this was very similar to the saddle node bifurcation in 1D. This is a 1D system. These are uncoupled systems. So this is like, I'll just say, interesting stuff happens here. So for example, for a greater than 0 in the system, I have fixed points and so these are the fixed points. Remember, there are no fixed points for a less than 0 because these guys are imaginary. So let's look at the Jacobian. How does the Jacobian look for the system? So I have the Jacobian as these guys. And if I evaluate it, it comes out to be minus 2x star 0, 0, minus 1. So that's the Jacobian, and the eigenvalues are essentially these guys. So as you can see, this is going to be for the fixed point at square root of a comma 0. This is going to be a stable node because both directions are leading to the fixed point. And I'll just draw it. So this is my phase portrait. This is y. This is x. I've got a fixed point here at I have a fixed point here at a comma 0. I have a fixed point here at 0. In the y direction, if you look at it, nothing happens. I mean, my eigenvalues is minus 1. So this is essentially the vector field is going this way. What about the x direction? X directions I have seen, this is a stable node, so things go over here. And for minus root a comma 0, this eigenvalue becomes positive. So I have a saddle here. So this fixed point is a saddle. This fixed point is a stable node. And I'll, as usual, have trajectories coming to the stable node from all directions. And over here I'll have those trajectories going this way. And that essentially is. And of course this is for a greater than 0. And for a less than 0, we don't have a fixed point. What happens to when I see not the phase space but the space of eigenvalues? I have the imaginary part of lambda, I have the real part of lambda, and I have two eigenvalues. I have minus 1 and I have got minus 2 root a. These are my eigenvalues. So you can see that for a is my parameter, and these are essentially the eigenvalues for the fixed point root a comma 0. Both lie on the negative real axis, and hence this point is all direction points towards the fixed point. That's essentially what's happening. I've already mentioned for a less than 0, you don't have a fixed point. What happens for a equals to 0? I'm slowly reducing a. These two fixed points keep coming near each other. That's the journey of the fixed points as I keep reducing a. And essentially at a equals to 0, I have, they both collide. this fixed point is coming this way. This fixed point, I should call it, not with a full color circle. This is actually a saddle. And these fixed points essentially collide for a equals to 0. And that's essentially what's happening. I have trajectories going this way, and in this direction I have trajectories repelling. So there's a merger of the fixed points, and in the space of the eigenvalues I have the imaginary lambda, I have the real lambda, and I have, of course, one of the eigenvalues is -1, and the other guy reaches here, and this is the point of bifurcation at a equals to 0. A greater than 0 has a different behavior than a equals to 0, and for a less than 0, I have y, I have x. I don't have a fixed point. But still, one can do a Jacobian analysis. So still the vector field looks like this. This is moving fast, and what happens is there's no fixed point, but the vector field is still here. This was in some sense the ghost. There used to be a fixed point there, and the trajectory is really slow down here. So slow bottleneck, I can say. And why is that so? Well, that's because I had this guy as this guy, and certainly a was less than 0, and I'm slowly reducing a. So for a equals to 0, this was still a fixed point. As a becomes less than 0, what really happens is I'm trying to figure out why does the trajectory, how can we see that the trajectories would really slow down as one is reaching 0. It's easy to see for a equals to 0. I'll have x dot equal to minus x square, and as x goes to 0, I'll have a real slowing down of x dot. It's going to be, the trajectory is going to be really slow out here. Is it easy to see for a less than 0? Okay, you guys think yourself. So similarly, I have a, the second case was a transcritical bifurcation, which was essentially the same thing which we discussed. So the canonical example of the transcritical bifurcation was ax minus x square, and y dot equals to minus y. Again, I think you guys can analyze it yourself. Here what is happening is that there is a single fixed point. So I have this guy as x a minus x. So I have got two fixed points essentially at 0, and this was at a. And for a greater than 0, this guy is stable and this guy was unstable. For a less than 0, it's the other way around. So there is essentially a change in stability for, remember we had this sort of a diagram where I had this fixed point suddenly becomes stable and this guy was stable and it becomes unstable. So this was a transcritical bifurcation. This was the journey of my two fixed points, so to speak, as I move the parameter. So this was x, and yeah, so that's essentially what's happening. And the y direction is always I have, so this was just my plotting x dot and x, but essentially you get the idea. If y direction is always nothing interesting is happening, it's always a contracting or an attracting direction. So that's the idea of what's happening in a transcritical bifurcation. And okay, so let's see what else. What about the pitchfork bifurcation? I'll just be back. Okay, so I think I can say this was, I think, parameter A, and for a less than 0, this is the journey of my fixed point. This was the x is x, and for a equals to 0, both the fixed points are the same, and for a greater than 0, they change stability. So this was the motion of the fixed points in the parameter space A. So pitchfork bifurcation is and as usual, this is the place where the interesting stuff is happening. The way I have designed these equations, y and x are decoupled. So what's going on? So I have the fixed points at x star equals to 0, and then I have it at x star equals to plus minus square root of a comma 0, So notice once again, for a less than 0, I have just one fixed point. These are imaginary. So, and that point is stable fixed point. This was the y direction and this is the x direction. And really, all the trajectories, everyone's happy. Everything is coming to the fixed point at x0, y0. And when I make a, so what's happening in the spectrum of the Jacobian? So the Jacobian, if I calculate, comes out to be a 0, 0, minus 1 at x equals to 0. And since a was less than 0, both the eigenvalues are negative. So in the spectrum of the eigenvalues, this is the imaginary part, this is the real part of the eigenvalue. This is minus 1, this is a. Both eigenvalues are negative, we are stable. And as I approach 0, as one approaches 0 for the parameter a, basically journey over here, two fixed points are about to be formed. Remember, because I get two fixed points, these guys, which are no longer going to be imaginary. So two fixed points are about to be born. So at a equals to 0, I really have still the one fixed point, and the trajectories look, they really come like this. Remember this behavior, because the trajectories have to be tangent to the direction with the lesser of the eigenvalues for t greater than infinity. So this is the asymptotically, and for t less than infinity, it's coming parallel to the direction of the greater eigenvalue. So this is essentially the critical slowing down. And the reason for that is that for a equals to 0, the equations of motion look like, so I had x dot was ax minus x cubed. For a equals to 0, that's nothing but this minus x cubed, this guy. Now if you look at it, this is a differential equation, and this is an example of an algebraic decay. So what's happening is that x would go, if you solve this, as square root of t plus c, something like that. So this is an algebraic decay, not exponential. As compared to when I have, let's say, this guy, well then I can safely say that my x goes as, when I solve this differential equation, this is exponential decay, which is a fast decay. So I really have, because a became 0, this is an algebraic decay, this is a critical slowing down that's happening over here. It's slowly approaching x equals to 0. And finally, for a greater than 0, I get this fixed point at x equals to 0 loses its stability because my Jacobian, I get one positive eigenvalue. So I have this as the repelling direction, and there are two more fixed points which are bound. Just as I had the pitchfork bifurcation. These are certainly stable ones. So this is the diagram of the phase space vector field in x and y, and so from one stable fixed point to three fixed points, and I have a pitchfork. This was a stable point, bond to stable, and this guy loses its stability, and this is an example of a super critical pitchfork bifurcation. Okay, so as a last part of this thing, let's just briefly discuss hop bifurcation, and then we are going to take it up next week. So in the hop bifurcation, that basically occurs when my eigenvalues are purely imaginary, or in our jargon, the trace of the Jacobian is 0, and the determinant of the eigenvalues is the product of the eigenvalues that's greater than 0. So essentially, in my trace determinant axis is somewhere here, which was somewhere on the center. So again, how bifurcation are, there can be supercritical Hopf bifurcations, there can be other kind of Hopf bifurcation. So essentially, when a stable spiral goes to an unstable spiral plus surrounded by a small amplitude limit cycle, that's essentially what's happening. So as an example, and this is what happens at the bifurcation, so let us look at it. This is r dot equals to ar minus r cube, and theta dot equals to omega plus br square. So if you look at it, essentially what's happening for a less than 0, I mean theta just provides this angular rotation part of it. For a less than 0, this is a stable point. This guy is stable. So I have a stable spiral. Everything is like this for a less than 0. And for a equals to 0, what happens is and that's the only fixed point in the game. For a equals to 0, I have r dot equals to minus r cube. By the way, this is still, notice this is algebraic decay in R. So it's still a very slow limit cycle. It's a very slowly decaying limit cycle. It's a blob which goes very, 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 very slowly towards the center. It's still a slow decaying spiral, and that can be seen from this equation. It's still declining because of the negative sign. And by the way, if I linearize these equations, r dot equals to ar minus r cube, theta dot equals to omega plus br square. I think we did this, but linearization is going to predict a center, which is incorrect. You know, we discussed centers are fragile is going to incorrectly predict a center. But you can see this is not a center. And then what happens for a greater than 0? A greater than 0, what happens to these equations? I have got something interesting happens. I have an unstable spiral surrounded by, so I'll just write it down as r a minus r square. That's my r dot. So I still have a fixed point at r equals to 0, but now that fixed point has become unstable. And so that's going to spiral outwards, and I have a limit cycle which is formed at r equals to square root of a. So essentially my stable fixed point for stable spiral for a less than 0 gave rise to a fixed point, unstable fixed point, and a small amplitude limit cycle as a goes to 0. So this is what's happening on the bifurcation. And a equals to 0 was still algebraic decay, and still it was a fixed point at r equals to 0. So that's an example of a supercritical Hopf bifurcation. We'll resume this in the next class. Other examples, and then of course these are all fixed point bifurcations. We still have to cover bifurcation of periodic orbits, etc. So that is for the next class. Okay, thank you. I'll just see if there's anything else remaining. Yeah, so you guys should convert these equations into Cartesian and do the Jacobian analysis and convince yourself that indeed linearization at a equals to 0 is indeed going to predict a center incorrectly. So please do that exercise as a homework. Thank you.